So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again.
James Webb is demonstrating that it is truly capable of the job it was built for, pushing the boundaries of astronomy and cosmology closer to the beginning of time, into the period when the first light from stars and galaxies cleared the thick fog that was obscuring our view of the universe. And it is doing so by providing us with jaw-dropping images of the cosmos since July 2022. So far, the powerful observatory is not only delivering on its promises, it is living up to the hype and its price tag too, by revolutionizing our understanding of the early universe. Having said that, with James Webb, we've come far enough to put together the broad strokes of how our universe grew up, and it's looking like a story that will lead to decades of additional research to robustly put all of the pieces together. The very first stars must have formed long before James Webb is observing, likely within a time period just 100 to 200 million years after the Big Bang. The earliest galaxies that we see are likely the brightest and most massive ones from their time, and they exist in great numbers, beyond 500 million years after the Big Bang, and quite abundantly even 300 to 400 million years after the Big Bang. Many galaxy candidates exist from when the universe was only 250 to 300 million years old, and there's every reason to hope that many of them will truly turn out to be confirmed galaxies once all is said and done. But when we look at these very early galaxies, we do get the impression that something is amiss. Many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. It's not that galaxies weren't forming back then, because they were. But they weren't like this. The ones spotted in this study are, as far previous research and models have told us, too red to be as bright as they are, and too bright to be as red as they are. Their bold color is what marks these galaxies as so old. As the universe expands and objects fly farther away from us faster and faster, the light they produce gets more and more stretched out, and the more stretched out light gets, the redder it looks. Objects moving towards us, on the other hand, look blue because their motion compresses light rather than stretching it out. This elongating of light is called redshift, and it's one of the ways astronomers date things in the universe. Things that are incredibly old, like these galaxies, have a very high redshift and appear bright red in observational data. But not only are these galaxies red, their brightness indicates that they're big. Way bigger than they should be. Calculations done by the research team suggest that these 6 galactic candidates are each about the size of our own Milky Way. And according to almost all of our best models, there just shouldn't have been enough stuff present in the universe that early to form these things. The objects are so impossible, in fact, that, according to a statement, the team has been informally referring to them as universe breakers. These galaxies disagree with about 99% of our current models of the early universe, demanding some serious reinvestigation into a matter many researchers thought was pretty much settled. As Joel Leja, one of the authors of the study, said in a press release, "What's funny is, we have all these things we hope to learn from James Webb, and this was nowhere near the top of the list. We've found something we never thought to ask the universe." In other words, the fact that James Webb saw so many galaxies with these properties so early on is puzzling. So we're wondering, do we really understand the early phases of the formation of these galaxies? And this has truly posed a lot of questions for the theorists. But what's at stake here is our modern understanding of the history of the universe, as encapsulated by the so-called lambda cold dark matter model, often abbreviated as LCDM. This model makes a few base assumptions, just like any other model in science. The model assumes that general relativity is correct at cosmological scales, and that our universe is homogeneous and isotropic, the same in all directions. It assumes that our universe is geometrically flat and that there is some entity, called dark matter, that doesn't often interact with normal matter. And it assumes that there's another substance, called dark energy, that maintains a constant density as the universe expands. Once those assumptions are set, and they are, based on numerous past observations, the LCDM has only 6 free parameters. You need to make various cosmological measurements to get those numbers, but once you do, the model can predict everything else about the universe, up to and including the present-day expansion rate. So here comes the tension. As Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, said, Webb's results are very surprising and hard to get in our standard model of cosmology. And it's probably not a small change. We'd have to go back to the drawing board. One controversial idea is modified Newtonian dynamics, or MOND, which posits that dark matter does not exist and that its effects can instead be explained by large-scale fluctuations in gravity. To date, James Webb's observations could support such a theory. According to McGaw, who is one of the idea's leading proponents, MOND has had a lot of its predictions come true. This is another one of them. However, others remain unconvinced. So far, everything that we've tried to test MOND hasn't been able to really provide a satisfactory answer, says Jehan Kartaltepe, an astrophysicist at the Rochester Institute of Technology. One simpler solution is that galaxies in the early universe could have little or no dust, making them appear brighter. This scenario could confound efforts to calculate the galaxy's true masses and could perhaps also explain A.L. May's difficulty spotting Glass Z13. As Andrea Ferrara, an astronomer at the Scuola Normale Superiore in Italy, who has proposed such a possibility, said, "It could be that supernovae didn't have enough time to produce the dust, or maybe in the initial phases of galaxy formation the dust is expelled from galaxies." Alternatively, many scientists believe that James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structures. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as-yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. But perhaps instead, these halos were simply more efficient at drawing in regular matter to feed star formation. According to Jorge Peñarrubia, a cosmologist at the University of Edinburgh in Scotland, this is probably telling us something about how stars form in dark matter halos early on. Today, our galaxy produces roughly 1 new star per year, but Marco Castellano's paper based on James Webb's first data suggests that star formation rates must have been at least 20 times higher in his and Naidu's 2 candidate galaxies. Another Webb-derived preprint paper posits that Milky Way-sized galaxies could have arisen just a 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan Colchin, such outsized rates of star formation stretch the boundaries of what is physically possible. If those values are correct, you'd need to have galaxies turning all their mass into stars and forming stars as fast as they could. A perhaps more plausible possibility is that stars were somehow more efficient at accumulating mass in the early universe. This would lead to bulkier, brighter stars, enhancing early galaxies' visibility to James Webb. Maybe you just create a whole load of very, very massive stars, says Stephen Wilkins, an astronomer at the University of Sussex in England. These could be so-called population 3 stars, the hypothesized first stars in the universe. Although astronomers have yet to conclusively observe such stars, there is plentiful circumstantial evidence for their existence. Emerging from the primordial hydrogen and helium gas that pervaded the early universe, population 3 stars would lack heavier elements, allowing them to reach humongous sizes, hundreds of times bulkier than our sun. But like the brightest, briefest candles, these stars' immensity would limit their lifetime to no more than a few million years, making their detection today difficult. However, it is possible that some of the more remote galaxies already found by James Webb, and those even more ancient that may still await discovery, could contain evidence for population 3 stars. the brightness of these galaxies could be attributed to such stars, which would be much hotter and brighter than subsequent population 2 stars and population 1 stars, such as our Sun, both of which fill our modern-day universe. But to find out for certain, James Webb will need to perform spectroscopic follow-up of these more distant galaxy candidates, a time-consuming process of gathering a rainbow-like spectrum from a galaxy's emitted light to work out which chemical elements are present in its constituent stars. One clear signature of population 3 stars could be a specific spectral feature of helium that could only arise within stars that are hotter than about 100,000 degrees Celsius. As such, what's interesting is such follow-up observations are set to begin imminently, and it's really worth waiting. Astronomers are now racing to conduct next observations with James Webb. More programs have been designed to hunt for distant galaxies, such as Webb, which aims to hugely increase the known population of early galaxies by observing a wider swath of sky for hundreds of hours. Future proposals might look for evidence of those first proto-galaxies, perhaps using the explosive deaths of supersized first stars in especially luminous and energetic supernovae as markers for their existence. Some estimates suggest James Webb could see as far as a redshift of 26, just 120 million years after the Big Bang, a cosmic blink of an eye. Much other work will be done to follow up the growing list of high redshift candidates. These would be quite amazing. At least, it would demonstrate we're not getting fooled. However, just a word of caution. It's more likely that the early universe is different from what we predicted. If James Webb finds that the apparent early burst of massive galaxy formation suddenly ebbed in subsequent cosmic epochs, this could suggest the universe was expanding faster than expected back then. Perhaps twice as fast as predicted by current consensus estimates. This could be linked to the influence of a particular and so far entirely hypothetical variety of dark energy, which is the enigmatic and mysterious force that appears to drive the accelerating expansion of the universe. So-called phantom models of dark energy allow its potency to fluctuate across cosmic time. If such models are valid, they suggest dark energy's influence on the universe's expansion could have been far greater shortly after the Big Bang than they are today. It's unsettling, isn't it? After all, such ideas, while seemingly far-fetched, cannot yet be entirely ruled out as astronomers continue to grapple with the prevalence of galaxy candidates in the early universe. At that time, having said that James Webb Telescope has ushered in a new era of science, and despite the uncertainties, the rapid communication of new discoveries has invigorated astronomers. As more data continues to pour in from the telescope, and as different teams using different observational schemes publish their results, we'll learn how to use James Webb even more efficiently and effectively. It's that glorious case where whenever we learn something new, the whole community benefits. With an expected lifetime that will take it well into the 2040s, we have decades of new science, new discoveries, and a new understanding of how the universe grew up to look forward to with great optimism. While there are still many mixed opinions about whether James Webb really overthrew the Big Bang Theory or not, new stunning observations of the cosmos is calling our current standard model of the cosmos into question. In other words, our cosmology may now be under serious threat. New observations of the cosmos have suggested that dark energy, the force causing our universe to expand faster and faster, seems to be weakening. That may not sound like much in and of itself, but this finding actually has the potential to cause the first major paradigm shift in cosmology since the discovery of the accelerated expansion of the universe just over 25 years ago. It could even suggest our universe won't end in a big rip or a big chill, but rather a big crunch. More on that shortly. First, let's dive into these fascinating results. The new clues about dark energy evolving came as part of one of the deepest maps of the cosmos ever created, built using the first year of data collected by the Dark Energy Spectroscopic Instrument, or DESI for short. The instrument's 5,000 robotic eyes collect light from millions of galaxies across over a third of the entire sky as we see it from Earth. This light is then broken down into a spectrum of colors, allowing scientists to measure the expansion of the universe over billions of years by measuring a change in light wavelength called redshift. Collected over no more than a fifth of DESI's mission operating time, data gleaned with the survey already promises major shakeups and has cosmologists excited about what comes next. As Luz Angela Garcia Peñalosa, former DC team member and a cosmologist at the Universidad ECC in Colombia, said, "The release of these results was a great day for cosmology, pointing to a decreasing effect of the dark energy over time, meaning it is evolving and, therefore, not constant after all. The discovery of evolving dark energy would be as revolutionary as the discovery of the accelerated expansion of the universe itself, if confirmed with future data." The LCDM model suggests that, immediately following the Big Bang, the universe was majorly dense and incredibly hot, but also remarkably smooth and more or less the same, or homogeneous, in all directions. As the universe expanded, small fluctuations in density began to appear, and these dense patches grew. Clumps of dark matter began to condense as the universe evolved, and newly formed atoms gathered and spurred gas molecules within these clumps. This resulted in a universe filled with little more than hydrogen and helium, the two lightest and simplest chemical elements, and dark matter. The bonding of electrons to protons to create the first atoms meant that light was suddenly free to travel, and this first light is seen today as the cosmic microwave background, fossil radiation that can tell us a lot about the history of the universe. Regions of higher density drew gas and dark matter together, forming the seeds for the first galaxies in the LCDM model that collapsed to birth proto-galaxies. In these early galaxies, the hydrogen and helium gas created the first stars. Finally, proto-galaxies and the halos around them merged to form larger and larger galaxies. Importantly, however, in this model, dark energy is represented by lambda, and lambda is supposed to be constant over time. However, according to the latest observation, DESI saw that the equation of state of the universe isn't consistent with the usual LCDM model, but instead, it is showing a hint that dark energy is varying with time. These findings open a window for variable dark energy models because they show a departure for the constant equation of state. This was pretty surprising because most cosmological observations thus far have favored the LCDM model. The entire cosmological community was really shocked. If these novel findings from DESI prove accurate, and they are currently extremely robust, it would appear, then the cosmological constant may no longer be a suitable representative for the mysterious force of dark energy. Some physicists may welcome doing away with the cosmological constant, however. Either way, not only has it been a headache for decades, but this wouldn't be the first time that our burgeoning understanding of the cosmos had warranted its disposal. The cosmological constant, represented by the Greek letter lambda, has posed quite the problem for physicists since the early 20th century. In 1915, Albert Einstein released what is arguably his most revolutionary theory, general relativity, which described gravity as a concept that emerges from the curvature of space and time, a curvature caused by bodies with mass. 2 years after this, in 1917, Einstein and Dutch astronomer Willem de Sitter demonstrated that the equations of general relativity could be used to describe the universe, albeit a highly simplified universe. However, there was a problem. The universe described by the equations of general relativity didn't describe a universe that sits still. At that time in physics, the general consensus was that the universe was static, neither expanding nor contracting, and Einstein agreed with that consensus. So he added a sort of fudge factor to his equations, the cosmological constant, or lambda. This balanced the universe, adding the right push and pull to keep it static. Around 12 years later, in 1929, Edwin Hubble was studying distant galaxies and found that light from them was being stretched, or redshifted. The further away a galaxy was, he saw, the greater this effect was. This indicated that the universe was not static, but was, in fact, expanding. Scientists would spend the next 7 decades trying to measure the rate of this expansion, determined by a value called the Hubble constant. No longer needing to describe a static universe, Einstein removed the cosmological constant from his equations of the universe. allegedly describing the introduction of lambda as his greatest blunder. But the cosmological constant wouldn't stay in the cosmic dustbin for long. Before the end of the 20th century, lambda would be back in a big way and with a new role. In 1998, two separate teams of astronomers were making observations of distant Type 1a supernovas and using them as cosmic distance measurements when they discovered that the expansion of the universe isn't actually slowing as one might expect. It's speeding up. Then, dark energy was introduced as a placeholder for whatever seems to be causing this accelerating expansion. But despite the fact that it makes up 70% of the universe's total matter and energy budget, nobody knows what it is. In many models of the cosmos, including the prevalent LCDM model, dark energy is represented by the rescued cosmological constant, or lambda, that's now acting to oppose gravity and push the very fabric of space and time apart at a quickening rate. Still, after being introduced as a value for the accelerating expansion of space, the cosmological constant remained a problem. Values delivered by observing distant supernovas and the value predicted by theories of quantum physics continue to vary wildly, diverging by as much as 10 to the power of 121, that is 1 followed by 121 zeros. To understand why dark energy and the accelerating expansion of the universe is so shocking, consider this very earthly analogy. Imagine giving a child on a swing one big push. That is analogous to the Big Bang, which kicked off the expansion of the universe. Over time, the swing would probably slow and reaches progressively lower points in its arc, right? That's akin to the expansion of the universe slowing down as the cosmos ages. But then, suddenly, without you applying a further push when the swing has almost come to a halt, imagine that it suddenly resumes moving. Not only this, but imagine that it swings faster and faster, reaching higher and higher points. That is equivalent to the action of dark energy that the cosmological constant is used to describe. It's no wonder scientists are eager to determine the cause of this extra cosmic push. The discovery that dark energy seems to be getting weaker adds a layer of complexity to the situation. As Garcia Peñalosa explained, this is a really good indication that maybe an LCDM model is not exactly the ultimate answer to the nature of dark energy. It's huge progress, but these results probably don't get us much closer to that answer. They are more telling us is more how to describe dark energy with a bearing to time, probably as a fluid that fills the universe and can be described with an equation of a state that is not constant. Returning to the swing analogy, discovering what caused the extra unseen push is critical to understanding the fate of the child on that swing. Will they land in the bushes, safely on the ground, or get launched into space? Similarly, understanding dark energy is critical because its evolution, or lack thereof, will determine the fate of the universe. One of the earliest proposed scenarios for how the universe ends is the Big Crunch. This theory suggests that the universe's current expansion, set in motion by the Big Bang approximately 13.8 billion years ago, could one day slow, stop, and reverse. In this scenario, the gravitational attraction of all the matter in the universe would eventually overcome the force driving its expansion. As a result, the universe would start to contract, with galaxies, stars, and planets gradually moving closer together. The Big Crunch scenario assumes a universe dense enough for gravity to dominate, eventually halting the universe's expansion. As the contraction continues, galaxies would collide, stars would merge, and the temperatures would rise due to increasing kinetic energy from collapsing matter. This contraction would continue, possibly leading to an environment similar to the one before the Big Bang, where all matter and energy were compressed into an extremely hot, dense point known as a singularity. However, the likelihood of the Big Crunch depends on the density of matter in the universe, often measured by the critical density parameter, omega, O. If omega is greater than 1, the gravitational pull would be strong enough to eventually reverse expansion, leading to a closed universe and the possibility of a Big Crunch. Observations from the cosmic microwave background radiation and other measurements suggest that omega is close to 1, indicating a flat universe where expansion might not reverse. Additionally, the discovery of dark energy, a mysterious force that appears to accelerate the expansion, complicates the prospects for a big crunch. The Big Freeze, also known as heat death, represents a scenario where the universe's expansion continues indefinitely. Unlike the Big Crunch, where gravity eventually overcomes expansion, the Big Freeze assumes that the current accelerated expansion will continue forever. In this scenario, galaxies, stars, and other cosmic structures drift farther and farther apart, effectively isolating them. As the universe expands, it cools, and as a result, galaxies will eventually exhaust their star-forming fuel. Stars will burn out, turning into white dwarfs, neutron stars, or black holes. Over trillions of years, these remnants will slowly decay or merge, leaving the universe largely devoid of any sources of light or energy. In the Big Freeze scenario, entropy or disorder will increase as the universe moves towards thermodynamic equilibrium. This means that all energy will be evenly spread out, and no more work or change can occur. The temperature throughout the universe will drop to nearly absolute zero as all forms of organized matter degrade. In this final state, only subatomic particles and photons would remain, dispersed across an incredibly vast and cold space. This idea aligns with the second law of thermodynamics, which states that entropy in a closed system tends to increase over time. A driving force behind the Big Freeze is the presence of dark energy. If dark energy's influence remains constant or increases, it will keep pushing galaxies apart, supporting a forever expanding universe and favoring heat death. Currently, dark energy is measured to constitute about 68% of the universe's total energy content, indicating it plays a significant role in the cosmos's fate. Thus, the Big Freeze is one of the more widely accepted scenarios among cosmologists. The Big Rip is a more dramatic and cataclysmic scenario compared to the Big Freeze and Big Crunch. In the Big Rip scenario, the expansion of the universe not only continues, but also accelerates exponentially, driven by a form of dark energy known as phantom energy. Unlike typical dark energy, which maintains a steady expansion rate, phantom energy would increase in density over time, causing the expansion to accelerate more and more. As the universe's expansion accelerates, it would begin to overcome all other forces, including gravitational, electromagnetic, and even atomic forces. In the final moments leading to the Big Rip, galaxy clusters would separate, galaxies themselves would be pulled apart, and stars and planets would disintegrate. Even molecules and atoms would eventually be torn apart by the overwhelming force of expansion. The Big Rip is an extreme scenario and depends on the exact nature of dark energy. For the Big Rip to happen, the dark energy equation of state, the ratio between the pressure of dark energy and its density, would need to be less than 1. Current observations place this value close to 1, but if it changes over time, the Big Rip could become a possibility. This model predicts a finite amount of time before the universe reaches its catastrophic end. Based on current estimates, if the Big Rip scenario were correct, it would occur approximately 22 billion years from now. However, much remains unknown about the nature of dark energy, so predictions around the Big Rip are still speculative. Another potential scenario suggests that the universe might undergo cycles of expansion and contraction, leading to a series of Big Bangs and Big Crunches. This cyclic model implies that the universe is not destined to end permanently, but will instead recollapse and re-expand in an endless loop of creation and destruction. In this model, each cycle would begin with a Big Bang, lead to an expansion phase, followed by a contraction leading to a Big Crunch, which then bounces back into another Big Bang. This idea avoids the problem of a singular beginning or end. Ancient philosophical ideas, as well as more modern theories in physics, have entertained the idea of a cyclic universe, though each cycle may differ due to changes introduced in each iteration. Physicists studying string theory and quantum gravity have proposed some mechanisms that could allow such a cyclical process. For instance, the concept of brain cosmology in string theory suggests that our universe could be a brain that collides with other brains, leading to repeated Big Bangs. While intriguing, cyclic models face challenges, especially when considering entropy. Each cycle would accumulate more entropy, meaning that unless there is a process to reset entropy, the universe would eventually reach a state of maximum entropy similar to the heat death described in the Big Freeze. Another possible scenario involves a phenomenon known as vacuum decay. This hypothesis is grounded in quantum field theory, which suggests that our universe could exist in a false vacuum state. In simple terms, a false vacuum is a local energy minimum, but not the true lowest energy state of the field. Over time, quantum fluctuations might trigger a transition to a true vacuum state, which could cause a catastrophic event that reconfigures the universe. If such a decay were to happen, a bubble of true vacuum would form and expand at nearly the speed of light, annihilating everything it encounters. Within this bubble, the laws of physics as we know them could change, potentially making life and matter impossible. This idea may sound like science fiction, but it is theoretically plausible based on our understanding of particle physics. The probability of vacuum decay is currently unknown, though calculations suggest it is an incredibly unlikely event within the lifetime of the universe. However, the possibility that our universe could shift to a true vacuum state represents an additional and unsettling scenario for the universe's ultimate fate. After all, the future of the universe, whether it ends in a big crunch, big freeze, big rip, or through more exotic phenomena like vacuum decay or cyclic rebirth, remains one of the greatest mysteries in cosmology. Each scenario carries profound implications, not only for science but also for philosophy and existential questions about humanity's place in the cosmos. The fate of the universe depends on complex factors including the properties of dark energy, dark matter, and the fundamental laws governing space and time. Advances in technology, such as improved telescopes and observational data, will continue to shed light on these mysteries. However, for now, each of these scenarios provides a window into the possibilities of our cosmic destiny, reminding us both of the vastness of the universe and the limits of human understanding. Whether the end comes through a slow freeze, a violent rip, or a rebirth, the exploration of the universe's fate connects us to the deepest questions about the nature of existence itself.
The Webb looks so far out that it's capturing light that's been travelling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang.
The universe has not existed forever. It was born. Around 1382 billion years ago, matter, energy, space, and time erupted into being in a fireball called the Big Bang. It expanded, and from the cooling debris, there congealed galaxies, islands of stars of which our Milky Way is one among about 2 trillion. This is the Big Bang theory. But the universe popping into existence out of nothing is so bonkers that scientists had to be dragged kicking and screaming to the idea. Even the physicist Brian Cox also said he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head.
A cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again.
Things got worse as James Webb, the most powerful space telescope, obtained some very strong evidence demonstrating that the Big Bang wasn't truly the start of it all. All begs the question, what happened before the Big Bang? And if the Big Bang wasn't the beginning, what was it? Join us as we shed some light on the origin of the universe. The first time the phrase the Big Bang was uttered was over 20 years after the idea was first described. Ironically, the term itself comes from one of the theory's greatest detractors, Fred Hoyle, who was a staunch advocate of the rival idea of a steady-state cosmology. In 1949, he appeared on BBC Radio and advocated for what he called the perfect cosmological principle, the notion that the universe was homogeneous in both space and time, meaning that any observer not only anywhere but anywhen would perceive the universe to be in the same cosmic state. He went on to deride the opposing notion as a hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past, which he then called irrational and claimed to be outside science. But the idea, in its original form, wasn't simply that all of the universe's matter was created in one moment in the finite past. That notion, derided by Hoyle, had already evolved from its original meaning. Originally, the idea was that the universe itself, not just the matter within it, had emerged from a state of non-being in the finite past. And that idea, as wild as it sounds, was an inevitable but difficult to accept consequence of the new theory of gravity put forth by Einstein back in 1915, general relativity. When Einstein first cooked up the general theory of relativity, our conception of gravity forever shifted from the prevailing notion of Newtonian gravity. Under Newton's laws, the way that gravitation worked was that any and all masses in the universe exerted a force on one another, instantaneously across space, in direct proportion to the product of their masses, and inversely proportional to the square of the distance between them. But in the aftermath of his discovery of special relativity, Einstein and many others quickly recognized that there was no such thing as a universally applicable definition of what distance was, or even what instantaneously meant with respect to two different locations. With the introduction of Einsteinian relativity, the notion that observers in different frames of reference would all have their own unique, equally valid perspectives on what distances between objects were and how the passage of time worked, it was only almost immediate that the previously absolute concepts of space and time were woven together into a single fabric, space-time. All objects in the universe moved through this fabric, and the task for a novel theory of gravity would be to explain how not just masses, but all forms of energy shaped this fabric that underpinned the universe itself. Although the laws that governed how gravitation worked in our universe were put forth in 1915, the critical information about how our universe was structured had not yet come in. While some astronomers favored the notion that many objects in the sky were actually island universes that were located well outside the Milky Way galaxy, most astronomers at the time thought that the Milky Way galaxy represented the full extent of the universe. Einstein sided with this latter view, and, thinking the universe was static and eternal, added a special type of fudge factor into his equations, a cosmological constant. Although it was mathematically permissible to make this addition, the reason Einstein did so was because without one, the laws of general relativity would ensure that a universe that was uniformly distributed with matter, which ours seemed to be, would be unstable against gravitational collapse. In fact, it was very easy to demonstrate that any initially uniform distribution of motionless matter, regardless of shape or size, would inevitably collapse into a singular state under its own gravitational pull. By introducing this extra term of a cosmological constant, Einstein could tune it so that it would balance out the inward pull of gravity by proverbially pushing the universe out with an equal and opposing action. But two developments, one theoretical and one observational, would quickly change this early story that Einstein and others had told themselves. In the 1920s, Belgian physicist and Catholic priest Georges Lemaitre proposed a revolutionary idea, that the universe began as a primeval atom, which then expanded to form everything in existence. In 1927, Lemaitre published a paper proposing that the universe was expanding, a theory he based on Einstein's general relativity equations. Although his work initially received little attention, it became one of the key foundations for the Big Bang theory. Lemaitre's insights suggested a universe that had a specific starting point in time, radically challenging the static universe model. Around the same time, American astronomer Edwin Hubble made a groundbreaking discovery at the Mount Wilson Observatory in California. Observing distant galaxies, he noted a redshift in their light, meaning that the wavelengths of light from these galaxies were stretched, indicating that they were moving away from Earth. Hubble's work provided empirical evidence for the expansion of the universe, bolstering Lemaitre's theoretical predictions. In 1929, Hubble's law emerged, establishing a linear relationship between the distance of a galaxy and its velocity of recession, a key component supporting the Big Bang model. Fast forward to the 1960s and 1970s, as well as ever since, a combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. The discovery of the cosmic microwave background and the subsequent measurement of its temperature and the black body nature of its spectrum eliminated alternative theories like the steady-state model. The measured abundances of the light elements throughout the universe verified the predictions of Big Bang nucleosynthesis, while also demonstrating the need for fusion in stars to provide the heavy elements in our cosmos. And the farther away we look in space, the less grown-up and evolved galaxies and stellar populations appear to be, while the largest scale structures like galaxy groups and clusters are less rich and abundant the farther back we look. The Big Bang, as verified by our observations, accurately and precisely describes the emergence of our universe, as we see it, from a hot, dense, almost perfectly uniform early stage. But what about the beginning of time? What about the original idea of a singularity and an arbitrarily hot, dense state from which space and time themselves could have first emerged? That's a different conversation today than it was back in the 1970s and earlier. Back then, we knew that we could extrapolate the hot Big Bang back in time, back to the first fraction of a second of the observable universe's history. Between what we could learn from particle colliders and what we could observe in the deepest depths of space, we had lots of evidence that this picture accurately described our universe. But at the absolute earliest times, this picture breaks down. There was a new idea, proposed and developed in the 1980s, known as cosmological inflation, that made a slew of predictions that contrasted with those that arose from the idea of a singularity at the start of the hot Big Bang. In particular, inflation predicted a curvature for the universe that was indistinguishable from flat to the level of between 99.99% and 99.9999%. Comparably, a singularly hot universe made no prediction at all. Equal temperatures and properties for the universe, even in causally disconnected regions. A universe with a singular beginning made no such prediction. A universe devoid of exotic high-energy relics like magnetic monopoles. An arbitrarily hot universe would possess them. A universe seeded with small magnitude fluctuations that were almost, but not perfectly, scale invariant. A non-inflationary universe produces large magnitude fluctuations that conflict with observations. A universe where 100% of the fluctuations are adiabatic and 0% are isocurvature. A non-inflationary universe has no preference. A universe with fluctuations on scales larger than the cosmic horizon. A universe originating solely from a hot Big Bang cannot have them. And a universe that reached a finite maximum temperature that's well below the Planck scale, as opposed to one whose maximum temperature reached all the way up to that energy scale. The first three were post-dictions of inflation. The latter four were predictions that had not yet been observed when they were made. On all of these accounts, the inflationary picture has succeeded in ways that the hot Big Bang, without inflation, has not. During inflation, the universe must have been devoid of matter and radiation and instead contained some sort of energy, whether inherent to space or as part of a field, that didn't dilute as the universe expanded. This means that inflationary expansion, unlike matter and radiation, didn't follow a power law that leads back to a singularity, but rather is exponential in character. One of the fascinating aspects about this is that something that increases exponentially, even if you extrapolate it back to arbitrarily early times, even to a time where TE, it never reaches a singular beginning. Now, there are many reasons to believe that the inflationary state wasn't one that was eternal to the past, that there might have been a pre-inflationary state that gave rise to inflation, and that, whatever that pre-inflationary state was, perhaps it did have a beginning. There are theorems that have been proven and loopholes discovered to those theorems, some of which have been closed and some of which remain open, and this remains an active and exciting area of research. But one thing is for certain, whether there was a singular ultimate beginning to all of existence or not, it no longer has anything to do with the hot Big Bang that describes our universe from the moment that inflation ended. The hot Big Bang occurred, the universe became filled with matter and radiation and more, and it began expanding, cooling, and gravitating, eventually leading to the present day. There are still a minority of astronomers, astrophysicists, and cosmologists who use the Big Bang to refer to this theorized beginning and emergence of time and space. But not only is that not a foregone conclusion anymore, but it doesn't have anything to do with the hot Big Bang that gave rise to our universe. The original definition of the Big Bang has now changed, just as our understanding of the universe has changed. If you're still behind, that's okay. The best time to catch up is always right now. Because James Webb, the supreme observatory that was built to revolutionize our understanding of the universe, is providing more and more evidence that the Big Bang wasn't really the beginning of it all. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope's giant segmented mirror and exquisitely sensitive instruments were designed to uncover details of cosmic dawn never before observed. Since it first started sending back science data in mid-2022, the internationally funded state-of-the-art telescope has been giving us images of distant galaxies that appear to have formed and matured far earlier than our models predicted. Webb's haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy predictions, with the dozens found so far. It's enough of a problem that some are calling it a challenge to our entire cosmic timeline. According to the standard model of cosmology, after the fiery Big Bang 13.8 billion years ago, the universe cooled, and energy turned into matter that eventually coalesced during the first few 100 million years, forming the first generation of stars and galaxies. Astronomers thought they had a decent understanding of this process. But Webb's results may suggest that stars and galaxies were forming far faster than anyone expected. The telescope had done nothing less, read the headlines then, break the universe, and upend models of cosmic history. Subsequent data have ruled out some of the more dramatic findings, and new simulations can accommodate at least a few of the strange observations. But some bright, massive, and early galaxies continue to confound theorists, suggesting that our understanding could shift in the coming years. According to Priyamvada Natarajan, a theoretical astrophysicist at Yale University in New Haven, Connecticut, no data at the moment has broken the universe, but I think there are interesting potential tensions emerging on different scales. Resolving these tensions will require researchers to revisit their fundamental assumptions about galactic evolution. That could mean bringing new ideas to the forefront, while leaving others in the cosmic dustbin. Prior to the launch of James Webb, no one knew if galaxies could even form so early in the universe's 13.8 billion year history, at a time when matter was thought to still be sedately coalescing into the gravitationally bound clumps required to give birth to large groups of stars. As Garth Illingworth, an astronomer at the University of California, Santa Cruz, said at a press conference held by NASA to announce the peer-reviewed validation of the first two candidates. And so we're wondering, do we really understand the early phases of the formation of these galaxies? This has posed a lot of questions for the theorists. Chief among them is how exactly dark matter guided the emergence of galaxies. For the first few 100,000 years after the Big Bang, the cosmos was so hot that gravity could not pull normal matter together to form large protogalactic clumps. But this was not an issue for dark matter, says Jorge Peñarrubia, a cosmologist at the University of Edinburgh in Scotland, because dark matter does not interact via electromagnetic forces. Instead, gravity alone is this invisible substance's master, meaning that in mere moments after the Big Bang, when primordial chaos otherwise reigned, gravity immediately began glomming together dark matter into large clumps known as halos. These dark matter halos are believed to have acted as gravitational sinks for normal matter, seeding the subsequent formation of galaxies in the early universe. The telltale motions of the stars they shepherd betray their endurance to this day. Such halos still surround galaxies like our own, majestic but invisible sculptors of the modern cosmos. James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structure. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as-yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. However, perhaps instead these halos were simply more efficient at drawing in regular matter to feed star formation. Today, our galaxy produces roughly one new star per year, but Castellano's paper suggests that star formation rates must have been at least 20 times higher in his and Naidu's two candidate galaxies. Another Webb-derived preprint paper posits that Milky Way-sized galaxies could have arisen just at 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan-Colchin, a cosmologist at the University of Texas at Austin, such outsized rates of star formation stretch the boundaries of what is physically possible. In the words of Boylan-Colchin, if those values are correct, you'd need to have our galaxies turning all their mass into stars and forming stars as fast as they could. Researchers have likened the impossible early galaxy problem to flipping through someone's old photo album, expecting to find baby pictures, and seeing a full-grown adult instead. With a person, you might just conclude that they're older than you thought, but with early galaxies, you very quickly run into a problem with the age of the universe itself. For generations, people argued over whether the universe had always existed, whether it had a beginning, or whether it was cyclical, with neither a beginning nor an end. But starting in the 20th and continuing into the 21st century, we not only drew a scientific conclusion to that question, the universe, as we recognize it, began with a hot Big Bang, but we were able to pinpoint precisely when that beginning occurred. The simplest and most straightforward way to measure the age of the universe is simply to look at the objects that are in it. Stars, for instance. We have hundreds of billions of stars in the Milky Way galaxy alone, and the overwhelming majority of the ancient history of astronomy was devoted to studying and characterizing stars. It remains an active field of research today, as astronomers have uncovered the relationship between observed properties of stellar populations and how old they are. The basic picture is that a cloud of cold gas collapses under its own gravity, leading to the formation of large numbers of new stars all at once that come in all different masses, colors, and brightnesses, and the largest, bluest, brightest stars burn through their fuel first. Therefore, when we look at a population of stars, we can tell how old it is by looking at what types stars still remain and what classes of stars are completely gone. Our galaxy has stars of all different ages in it, but the measurements of any individual star will be riddled with uncertainties. The reason is simple. When we view an individual star, we see it as it is today. We cannot see or know what happened in that star's past history that may have led to its present condition. We can only view a present-day snapshot of what exists and have to infer the rest. You'll often see attempts made to measure the age of an individual star, but that always comes along with an assumption that the star didn't have an interaction, merger, or other violent event in its past. Because of that possibility, and the fact that we only see the survivors when we look at the universe today, those ages always come along with massive uncertainties, on the order of 1 billion years or even more. However, the uncertainties are much smaller when we look at large collections of stars. The collections of stars that form within a galaxy like the Milky Way, open star clusters, typically contain a few thousand stars and only last a few 100 million years. The gravitational interactions between these stars eventually cause them to fly apart. While a small percentage last 1 billion years or even a few billion years, we have no known open star clusters that are even as old as our own solar system. However, globular clusters are larger, more massive, and more isolated, found throughout the halo of the Milky Way and most large galaxies. When we observe them, we can measure the colors and brightnesses of many of the stars inside, enabling us, so long as we understand how stars work and evolve, to determine the ages of these star clusters. Although there are uncertainties here as well, there is a large population of globular clusters, even within the Milky Way alone, with ages of 12 billion years or more. How certain are we of these figures? It's tough to say. While it's almost guaranteed that the oldest of these star clusters must be between 12.5 and 13 billion years old, there remain large uncertainties about the amount of time required for a star right around the mass of our Sun to begin its transition into a subgiant, followed by its transformation into a full-blown red giant star. It could be 10 billion years, it could be 12 billion years, it could be some value in between. For years, many astronomers who worked on globular clusters argued that the oldest ones were 14, maybe even 16 billion years old. But a shift in our understanding of stellar evolution now disfavors that interpretation of the data. Today, we can reliably conclude there's a lower limit to the age of the universe of around 12.5 to 13 billion years from the stars we measure. But that doesn't pin down the age precisely. It's a good constraint to have, but to arrive at an actual figure, we'd like a better method. Fortunately, the universe gives us one. You see, Einstein's general relativity, for a universe filled with even amounts of matter and energy everywhere and in all directions, gives a straightforward relationship between two quantities: the amounts and types of matter and energy present within the universe, and how fast the universe is expanding today. This relationship was first derived all the way back in 1922 by Alexander Friedmann, and the equations that enable us to derive how old the universe must be are known as the Friedmann equations. It took us many years to measure the constituents of the universe, but a consensus picture has emerged. Observations ranging from the abundances of the light elements to the clustering of galaxies to how galaxy clusters collide to distant supernovae to the fluctuations in the cosmic microwave background all point toward the same universe. In particular, it's made up of 68% dark energy, 27% dark matter, 4.9% normal matter, 0.1% neutrinos, 0.01% photons, and less than 0.4% of everything else, including spatial curvature, cosmic strings, domain walls, and other fanciful, exotic components. This picture agrees with the full suite of observations that we have. You have to really cherry-pick your evidence very hard, overemphasizing measurements with large ambiguities while simultaneously ignoring large suites of data, to wind up with sets of values that vary significantly from this. So then, you might think that everything hinges on the expansion rate. If you can accurately measure that, you can simply do the math and precisely arrive at the age of the universe. Beginning the early 2000s and ever since, the best data we have comes from the cosmic microwave background, first from WMAP, then from Planck, and as of July 14, 2020, from the Atacama Cosmology Telescope as well. Those values have all converged on the same expansion rate, 68 kilometers SSMPC, with an uncertainty of just 1 to 2%. When you calculate what that means for the age of the universe, you get a very robust 13.8 billion years, completely consistent with everything we know about stars. Hang on a second, though. You might have heard, and rightly so, that there's a controversy over this. While teams using the cosmic microwave background might all obtain one value for the expansion rate, and teams measuring the large-scale structure of the universe might agree, other methods yield a wildly different value. The other methods, rather than beginning with an early imprinted signal and measuring how it appears today, begin close by and work outward. They measure distances and the apparent recession speeds of various objects, a method generally known as the cosmic distance ladder. When you look at the distance ladder measurements, they all appear to give systematically higher values, between 72 and 76 kilometers SSMPC, about 9% higher, on average, than the value you get from the cosmic microwave background. You might think then that someone's right and someone's wrong. If the distance ladder team is correct and the cosmic microwave background team is wrong, then perhaps the universe is 9% younger than we think, just 12.8 billion years old. But that's not how it works in practice. The data from the cosmic microwave background isn't something that can just be ignored. It's something that must be reckoned with. The peaks, valleys, and wiggles that we see in its temperature fluctuations are a reflection of all these different parameters combined. Sure, the best fit values are for a universe expanding at 68 km SSMPC and with 68% dark energy, 27% dark matter, and 5% normal matter. But those can be varied, so long as they all vary together. Although it doesn't fit the data quite as well, you can up the expansion rate to, say, 74 km SMPC, and still arrive at a very good fit, so long as you're willing to change the relative fractions of dark matter and dark energy. With a little less dark matter, 20%, and a little more dark energy, 75%, a substantially higher expansion rate can still fit the data well, although not quite as well as the consensus values. However, what's fascinating about this is that the derived age barely changes at all. If you explore the full range of what is and isn't allowed, that 13.8 billion-year-old figure only comes along with an uncertainty of about 1%, between 13.67 and 13.95 billion years. But it's true that there are still many mysteries left to be uncovered about the universe. We don't know how fast the universe is expanding, and we don't know why different methods of measuring the expansion rate give such wildly different results. We don't know what dark matter or dark energy are, or whether general relativity, from which all this is derived, is still valid on the largest of cosmic scales. We don't even know exactly how much of the universe is locked up in which form of energy. It could have more dark matter and less dark energy than we think, or vice versa. The uncertainties are substantial. Similarly, we know that the universe is approximately 13.8 billion years old, but its exact age is not yet clear. Even today, the matter remains open to discussion, as new research could at any moment upend our previous cosmic conception for the age of the billions of galaxies that comprise our universe. That's what happened recently, when a new study based on James Webb's data was released, challenging the long-held notion that our universe is nearly 13.8 billion years old. If the findings of this latest research prove accurate, the Big Bang may have taken place 26.7 billion years ago, making the actual age of the universe nearly twice as old as we thought. According to Rajendra Gupta, a theoretical physicist at the University of Ottawa who authored the study with the new model, we can explain the conundrum that has long puzzled scientists about these ancient galaxies. That's because Gupta's newly devised model stretches the galaxy formation time by a several billion years. This age estimate is derived from the universe's expansion rate by measuring the redshift of spectral lines in the light emitted by distant galaxies. The redshift of light is what has long helped to inform physicists' estimates of the universe's age. In simple terms, the thought has been that the redshift indicated the distance of stars and galaxies, and hence, the faster they are moving away from Earth. By estimating the rate at which the stars are moving away, scientists can calculate how fast space is expanding into an infinitely growing universe. But the so-called tired light theory that originated in 1929 with Swiss astronomer Fritz Zwicky offered an alternative explanation. Perhaps the redshift we see isn't due to galaxies moving away from us. Instead, Zwicky's hypothesis was that it might be because light loses its energy and shine after traveling a long distance. Gupta proposes that if we allow Zwicky's theory to coexist with the idea of an expanding universe, we can reinterpret the redshift as a hybrid of both of these phenomena and thus arrive at an even more accurate age estimate of the universe. And Gupta goes even further in the study, introducing the fundamental physics idea from English theoretical physicist Paul Dirac, that coupling constants govern the interactions between particles. What does that mean? If these constants evolve, then the time it takes for the early galaxies observed in the Webb telescope to form extends from a few 100 million years to several billion years. Better put, it would offer an explanation for the advanced level of development and mass observed in the previously puzzling early galaxies. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
Located just 4.24 light-years from Earth, Proxima b represents one of the most exciting prospects for finding life beyond our solar system. This exoplanet orbits within the habitable zone of its parent star, raising the tantalizing possibility that it could host conditions favorable for life. However, while the promise of Proxima b is immense, numerous challenges complicate our understanding of this distant world. But now, with the addition of the James Webb Space Telescope, a technological marvel that has pushed the boundaries of astronomical observation, we have just achieved a groundbreaking feat: the clearest image of Proxima b ever seen. And that could change everything we think we know about our closest exoplanet neighbor. Join us as we dig deep into the most intriguing revelations of Proxima b and what they might reveal about the potential for life beyond. Let's start with an overview of Proxima b. This world was discovered by astronomers using the radial velocity method, which detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method provided strong evidence for the existence of a planet about 1.17 times the mass of Earth, orbiting Proxima Centauri every 11 days. This close proximity to its parent star places Proxima b within the so-called habitable zone, the region around a star where liquid water could exist on a planet's surface. Given that water is a key ingredient for life as we know it, the planet's location immediately sparked excitement about its potential to host life. Proxima b's discovery was especially significant because Proxima Centauri is the closest known star to the Sun, making its planetary system one of the most accessible in terms of future space exploration. This proximity has opened up possibilities for more detailed study and has led to bold proposals for missions to send probes to the Proxima system in the coming decades. Despite its closeness, Proxima b remains a deeply mysterious world. Classified as a red dwarf star, Proxima Centauri is significantly smaller and cooler than our Sun. And while red dwarfs are the most common type of star in the galaxy, they present unique challenges for planets that orbit them. One of the most intriguing aspects of Proxima b's mystery lies in the nature of its star. Proxima Centauri is known to be highly active, emitting frequent and intense stellar flares that could have profound effects on Proxima b. These flares, composed of radiation and charged particles, might strip away a planet's atmosphere over time, rendering it inhospitable. For Proxima b, which orbits just 0.05 astronomical units from its star, about 1/20th the distance between Earth and the Sun, the threat from such flares is a serious concern. The planet is likely tidally locked, meaning one side always faces the star while the other remains in perpetual darkness, creating extreme temperature differences. This leads to one of the major questions surrounding Proxima b. Can it sustain an atmosphere under such harsh stellar conditions? If Proxima b has lost its atmosphere, it would likely be a barren, lifeless world. However, some models suggest that it could retain a thick enough atmosphere to protect the surface from radiation. Alternatively, if Proxima b has a magnetic field similar to Earth's, it could shield the planet from these harmful effects. Determining whether Proxima b has an atmosphere and, if so, what it consists of, is one of the most pressing challenges for astronomers. Proxima b's location in the habitable zone suggests that liquid water might exist on its surface, but the conditions required for habitability are far more complex than simple proximity to a star. The intense stellar activity of Proxima Centauri, combined with the possibility of tidal locking, complicates the question of habitability. In the tidally locked scenario, one side of Proxima b would be bathed in constant daylight, while the other would be trapped in eternal night. The terminator line, the boundary between the day and night sides, might be a region where temperatures are moderate enough for water to exist in liquid form. This strip of twilight could potentially support life, but much depends on the planet's atmospheric dynamics. If the atmosphere is capable of redistributing heat from the day side to the night side, it might create a more temperate climate overall. However, if the atmosphere is thin or non-existent, the surface could be frozen on one side and scorched on the other. The composition of Proxima B's surface is another enigma. Is the planet rocky, like Earth, or is it covered in oceans or ice? Spectroscopic studies using powerful telescopes like the James Webb Space Telescope could eventually provide clues about the planet's composition, but as of now, scientists can only speculate. Some models suggest that Proxima b could have a significant amount of water, possibly as much as several Earth oceans, but this remains unconfirmed. Even if Proxima b has the right conditions for life, detecting signs of life from Earth presents significant challenges. Direct imaging of the planet is difficult due to its proximity to Proxima Centauri and the faintness of the light it reflects. Instead, astronomers rely on indirect methods, such as studying the planet's atmosphere for biosignatures, chemical markers like oxygen, methane, or other compounds that might indicate the presence of life. The James Webb Space Telescope plays a crucial role in these efforts. As the most powerful space observatory ever built, James Webb represents a leap forward in space exploration technology. Equipped with a massive 6.5-meter primary mirror and 4 sophisticated instruments, the telescope is capable of capturing the most distant and faint objects in the universe. Its infrared vision allows it to peer through cosmic dust and gas, revealing stars, galaxies, and planets with exceptional clarity. For Proxima b, James Webb's infrared capabilities are particularly crucial. Proxima Centauri is a red dwarf star, which emits most of its energy in the infrared spectrum. Proxima b, orbiting close to this star, is subject to these infrared emissions, making it an ideal candidate for Webb observations. Unlike previous telescopes that relied on visible light, James Webb can examine the heat signatures of Proxima b, providing new insights about this intriguing world. One of Webb's primary objectives in studying Proxima b is to analyze its atmosphere. Determining whether Proxima b has a thick, stable atmosphere is critical for understanding its potential to support life. Red dwarf stars like Proxima Centauri are notorious for emitting strong solar flares and ultraviolet radiation, which can strip a planet's atmosphere over time. If Proxima b has managed to hold on to its atmosphere, it would be an extraordinary discovery, indicating that planets around red dwarfs might be more resilient than previously thought. James Webb employs a technique known as transmission spectroscopy to investigate Proxima b's atmosphere. As the planet passes in front of its star, light from Proxima Centauri filters through the planet's atmosphere, allowing scientists to analyze the different wavelengths absorbed by various gases. By examining the light spectrum, James Webb can identify the presence of molecules like carbon dioxide, methane, and even water vapor, which are key indicators of habitability. The telescope's infrared capabilities are particularly advantageous for this task. Previous missions, such as the Hubble Space Telescope, were limited in their ability to detect atmospheric compositions due to their reliance on visible and ultraviolet light. James Webb, with its focus on infrared, can detect the thermal signatures of gases even in cooler atmospheres like that of Proxima b. The ultimate goal in studying exoplanets like Proxima b is to search for signs of life. While discovering an atmosphere would be a significant achievement, the detection of biosignatures, gases, or chemical compounds that suggest biological activity would be even more profound. James Webb is equipped to look for gases like oxygen, ozone, and methane, which could indicate the presence of life. Oxygen is a particularly strong biosignature, as it is typically produced by photosynthetic organisms. If the telescope detects oxygen in Proxima b's atmosphere, it would suggest that life, at least in some form, could exist on the planet. Methane is another important biosignature. While methane can be produced by geological processes, it is also a byproduct of biological activity on Earth. The simultaneous detection of methane and oxygen would provide compelling evidence for life. Moreover, Webb's ability to detect water vapor is critical for assessing Proxima B's habitability. Water is a fundamental requirement for life as we know it, and its presence in Proxima B's atmosphere or on its surface would increase the likelihood that the planet could support life. Webb's instruments are sensitive enough to detect even small amounts of water vapor, making it a powerful tool in the search for habitable worlds. While atmospheric composition is essential for determining Proxima B's habitability, understanding its surface conditions is equally important. The Webb telescope aims to provide insight into whether Proxima B's surface resembles that of Earth or if it is more hostile. Factors such as surface temperature, atmospheric pressure, and the presence of liquid water are all critical in assessing Proxima B's potential for hosting life. As told, Proxima B is tidally locked, meaning that one side of the planet always faces its star, while the other side is in perpetual darkness. This could lead to extreme temperature differences between the two hemispheres. The side facing Proxima Centauri may be scorching hot, while the dark side could be frigid. However, if Proxima B has a thick atmosphere, it could help distribute heat more evenly across the planet, potentially creating more stable conditions conducive to life. James Webb will measure the planet's heat signature using its mid-infrared instrument, or known as MIRI, which is capable of detecting thermal radiation emitted by Proxima B. By studying the planet's temperature distribution, James Webb can provide clues about the composition and thickness of its atmosphere, as well as the possibility of liquid water on the surface. Studying Proxima B is not only important for understanding this particular exoplanet, but also for gaining insight into the broader context of planetary systems around red dwarf stars. Red dwarfs make up about 70% of the stars in the Milky Way, and many of them are known to host planets. If James Webb finds that Proxima B is potentially habitable, it could suggest that habitable planets around red dwarfs are more common than previously thought. On the other hand, if Proxima B is found to be uninhabitable due to the harsh conditions imposed by its parent star, it would reinforce the idea that planets around red dwarfs face significant challenges in retaining their atmospheres. In either case, Webb's observations will provide valuable data that can be applied to other exoplanetary systems, helping scientists refine their models of planetary habitability. In short, the James Webb Space Telescope's exploration of Proxima B represents a new chapter in the study of exoplanets. With its advanced capabilities, James Webb is poised to provide unprecedented insight into the atmosphere, surface conditions, and potential for life on Proxima B. While many questions remain unanswered, the tantalizing possibility that it could harbor life or provide a secondary home for humanity has driven interest in developing the means to reach it. However, let's first accept that while 4 light years may seem close compared to the vastness of space, it is an almost unimaginable distance in practical terms. Current human-made spacecraft, like the Voyager probes, travel at speeds of around 17 kilometers per second. At that speed, it would take over 70,000 years to reach Proxima B. Clearly, we need a radically new approach to interstellar travel. To make the journey within a human lifetime, the spacecraft must travel at a significant fraction of the speed of light. Achieving this will require technological breakthroughs in propulsion, energy generation, and spacecraft design, all of which are currently in their infancy. One of the major barriers to interstellar travel is the lack of a feasible propulsion system. Traditional rocket propulsion, which relies on chemical reactions, is insufficient for the vast distances involved in a journey to Proxima B. New propulsion systems will be needed, and several promising concepts have been proposed. 1. Nuclear propulsion. Nuclear propulsion, both fission and fusion-based, could offer a way to achieve higher speeds than chemical rockets. In a nuclear fission system, atoms of uranium or plutonium are split, releasing energy that could be used to propel a spacecraft. Theoretically, nuclear propulsion could achieve speeds up to 10% of the speed of light, making the trip to Proxima b in about 40 years. Fusion propulsion, which mimics the process that powers the Sun, offers even greater potential. In a fusion reaction, atoms of hydrogen are fused together to create helium, releasing vast amounts of energy. While the technology to build a working fusion engine does not yet exist, it holds the promise of higher efficiency and faster speeds than fission, potentially reaching 20% of the speed of light. This would reduce the travel time to around 20 years. 2. Laser-powered light sails. Another innovative concept is the use of light sails powered by laser beams. This idea is central to the breakthrough Starshot project, an initiative proposed by billionaire Yuri Milner and supported by scientists such as Stephen Hawking. The project envisions tiny, lightweight spacecraft equipped with reflective sails that could be propelled by powerful lasers fired from Earth or from space-based stations. These laser-powered sails could, in theory, accelerate the spacecraft to around 20% of the speed of light, allowing them to reach Proxima b in just over 20 years. The key advantage of this system is that the spacecraft does not need to carry its own fuel, significantly reducing its mass. However, the engineering challenges are immense, including the need for an array of lasers powerful enough to propel the spacecraft and the difficulty of steering the light sail across vast distances. 3. Antimatter propulsion. Antimatter propulsion, while still highly speculative, offers the most efficient means of space travel known. When matter and antimatter collide, they annihilate each other, releasing 100% of their energy. In comparison, nuclear fission and fusion release only a tiny fraction of the energy locked within atoms. An antimatter-powered spacecraft could theoretically travel at speeds approaching the speed of light, making the trip to Proxima b in under a decade. However, producing and storing antimatter in the quantities needed for space travel is far beyond current capabilities. The energy required to create even a tiny amount of antimatter is astronomical, and the cost of producing just a few grams would bankrupt any nation. However, even if we solve the propulsion problem, there are enormous challenges associated with sending humans on such a long journey. The voyage to Proxima b would likely take decades, even with the most advanced propulsion systems. This raises several key concerns. 1. Human lifespan and aging. If a mission to Proxima b takes decades, we must address the problem of human aging and lifespan. One option is to send multiple generations of humans on a generation ship, where the original crew's descendants would complete the journey. However, this raises social and ethical questions about the nature of life on a spaceship, where entire generations would be born, live, and die without ever setting foot on Earth or the destination planet. Another possibility is cryogenic suspension, freezing the crew members for the duration of the journey and then reviving them upon arrival. While this technology is far from mature, research in cryopreservation is ongoing, particularly in the field of medicine. Achieving reliable and safe cryogenic sleep for humans would be a major breakthrough for interstellar travel. 2. Radiation and space environment. Space is a hostile environment. Beyond the protection of Earth's magnetic field, astronauts would be exposed to dangerous levels of cosmic radiation, which can cause cancer and other health issues. A journey to Proxima b would require advanced shielding technologies to protect the crew from this radiation. Additionally, the spacecraft would need to be completely self-sustaining, as resupply missions would be impossible. This means it would need to generate its own oxygen, food, and water for the duration of the trip. Closed-loop life support systems, which recycle waste into usable resources, will be essential. NASA is already developing such systems for long-term missions to Mars, but they would need to be scaled up and perfected for an interstellar journey. 3. Psychological and social issues. The isolation and confinement of space travel can have severe psychological effects. On a journey lasting decades, maintaining the mental health of the crew will be a significant challenge. Space travelers would be cut off from the rest of humanity, and the stress of living in close quarters with the same people for years could lead to interpersonal conflicts. Ensuring the well-being of the crew will require careful selection of personnel, comprehensive psychological support, and perhaps even virtual reality systems to simulate a more varied environment. Alternatively, robotic or artificial intelligence, also known as AI, crew members, could be used to minimize the psychological burden on human travelers. Given the dangers and challenges of sending humans to Proxima b, some have proposed that the first missions should be conducted by robotic probes. Advances in AI and robotics could allow for autonomous spacecraft capable of conducting scientific research, scouting the planet for potential habitability, and sending data back to Earth. A robotic mission could pave the way for human exploration, providing vital information about Proxima b's atmosphere, geology, and potential for life. These probes could also set up infrastructure, such as automated habitats or resource extraction systems that humans could later use when they arrive. Beyond the practical challenges of interstellar travel, there are more speculative ideas that could one day revolutionize our ability to traverse the stars. Warp drives and wormholes are concepts rooted in the theories of general relativity and quantum mechanics. While currently the stuff of science fiction, they represent potential shortcuts through space. Warp drives, first made famous by science fiction like Star Trek, propose a method of FTL for faster-than-light travel that doesn't violate the laws of physics. In 1994, theoretical physicist Miguel Alcubierre developed a model for a warp drive based on Einstein's equations. The Alcubierre drive proposes creating a bubble of space-time around a spaceship, contracting space-time in front of the ship while expanding it behind. This bubble would effectively move the spaceship faster than light without the craft itself exceeding the speed of light, a key requirement, since nothing can move faster than light within space-time according to Einstein's special relativity. The idea of the warp drive hinges on the concept of space-time manipulation. Space-time, according to Einstein's general theory of relativity, is malleable and can be stretched or contracted by mass and energy. In theory, by creating a region of contracted space in front of a spacecraft and an expanded region behind it, the craft could ride this wave and traverse vast distances at superluminal speeds without violating any physical laws. Essentially, the spacecraft would remain stationary within its bubble while the space around it moves. The Alcubierre drive is a speculative concept, and its practicality faces several monumental challenges. One issue is the enormous amounts of energy required. Early estimates suggested that the amount of energy needed to create a warp bubble would be equivalent to the mass energy of an entire planet. However, some later studies have refined these calculations, suggesting that the energy requirements might be reduced if we use exotic matter, a theoretical substance that has negative energy density. Though the warp drive remains theoretical, there have been advances in understanding the mathematics and physics behind it. In 2021, a group of researchers claimed to have found a new solution to the Alcubierre metric that significantly reduced the energy requirements, bringing the idea closer to feasibility. This research suggests that the warp drive might be achievable without violating known physical laws, but it would still require exotic materials and advanced technology far beyond our current capabilities. Another problem with the warp drive is how to generate and control the warp bubble. This would involve manipulating space-time itself, something that, as of now, we have no practical means to accomplish. Additionally, the presence of exotic matter, which has not yet been discovered, is crucial for maintaining the negative energy densities required for the warp bubble. Despite these challenges, the possibility of FTL travel using a warp drive is a tantalizing concept that continues to inspire researchers. Another promising concept for revolutionizing space travel is the idea of wormholes. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel through spacetime that connects two distant points. Wormholes would allow a spacecraft to travel enormous distances in a short amount of time by passing through a shortcut in spacetime. Like warp drives, the idea of wormholes comes from Einstein's theory of general relativity. In 1935, Einstein and physicist Nathan Rosen used the equations of general relativity to propose the existence of bridges through spacetime, wormholes. These wormholes could, theoretically, connect two distant locations in the universe, enabling instantaneous travel between them. The most well-known type of wormhole in theoretical physics is the traversable wormhole, first described by physicist Kip Thorne in the 1980s. A traversable wormhole would allow for safe passage from one end to the other, unlike many of the other solutions that lead to singularities or collapse too quickly to be useful. One of the main challenges in creating a wormhole is that it would require exotic matter with negative energy to keep it open. Like the warp drive, the existence of such exotic matter has not been confirmed. Without negative energy, a wormhole would collapse on itself before anything could pass through. This negative energy requirement is a significant hurdle, but it doesn't render the idea of wormholes impossible. In fact, quantum field theory allows for the existence of negative energy in small quantities, as seen in the Casimir effect, which raises the possibility that future advances in quantum physics could provide a way to stabilize wormholes. If wormholes can be created and stabilized, they could enable instantaneous travel between distant points in space. For example, a wormhole connecting our solar system with another galaxy would allow for immediate travel across vast distances that would otherwise take millions of years using conventional propulsion systems. Wormholes also raise intriguing possibilities for time travel. Since wormholes link two points in space-time, they could, in theory, be used to travel through time as well as space. This has led to some speculative theories about using wormholes as time machines, though the physics of time travel is even more speculative and fraught with paradoxes. In short, traveling to Proxima b is an extraordinary challenge, but it is not beyond the realm of possibility. With advancements in propulsion technology, human biology, and spacecraft design, the dream of interstellar travel could become a reality within the next few centuries. Although the technical and logistical obstacles are daunting, the desire to explore and expand beyond our solar system is a powerful motivator. As we stand on the threshold of becoming an interstellar species, Proxima b serves as both a destination and a symbol of humanity's enduring quest for knowledge and exploration. One day, perhaps, we will look back on this time as the moment we first began our journey to the stars. And what's notable, besides Proxima b, there are also other notable potential homes beyond Earth. And here is a quick look at the most promising exoplanets that scientists believe could harbor life or offer clues to the formation of planetary systems. The TRAPPIST-1 system, located 39 light-years away in the constellation Aquarius, has become a focal point in the search for habitable worlds. It consists of 7 rocky planets, 3 of which, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, are located in the star's habitable zone. What makes this system especially remarkable is that all 7 planets are roughly the size of Earth, and are in such close proximity to one another that an observer on one planet could likely see the others in the sky. The TRAPPIST-1 star is a red dwarf, much cooler and dimmer than our Sun, allowing the planets to orbit much closer to the star without experiencing extreme heat. This compact arrangement also means that studying the system is easier. Scientists can observe how the planets interact gravitationally, giving insights into their masses and compositions. TRAPPIST-1e, in particular, has emerged as a standout candidate for habitability. Its location in the middle of the habitable zone means it might have liquid water on its surface. Moreover, it is dense enough to suggest a rocky composition similar to Earth's. While the system's planets likely experience tidal locking, there's potential that atmospheric circulation could distribute heat, making parts of the planets temperate and potentially habitable. Elsewhere, LHS 1140b is also a top candidate. Discovered in 2017, LHS 1140b is a super-Earth orbiting a red dwarf star about 49 light-years from Earth. This rocky planet is about 1.4 times the size of Earth, but has 6 times our planet's mass, suggesting it is exceptionally dense. LHS 1140b orbits its star at just the right distance to lie within the habitable zone, making it a promising candidate for habitability. What sets LHS 1140b apart is its atmosphere. Scientists have detected a potentially thick atmosphere that may protect the planet from harmful radiation and maintain surface temperatures that could support liquid water. Given its mass and size, the planet's gravity could help it retain this atmosphere even under the bombardment of radiation from its star. This exoplanet's relatively short distance from Earth and the presence of a dense atmosphere make it a target for further exploration, particularly with instruments like James Webb, which can analyze its atmospheric composition in detail. If it harbors signs of water vapor or even biosignatures like oxygen, it could be one of the most exciting discoveries in exoplanet science. Kepler 452b, discovered by NASA's Kepler mission, has been dubbed Earth's cousin because of its size and location in the habitable zone of a sun-like star. Located 1,400 light-years away, Kepler 452b is about 60% larger than Earth and orbits a G-type star similar to our Sun, although it is slightly older. The age of Kepler 452b's star, estimated to be 6 billion years, raises fascinating questions about the planet's evolutionary path. If Kepler 452b had conditions conducive to life in its past, it may have supported life for billions of years, giving it a significant evolutionary head start compared to Earth. However, its older star also means that it is likely to be experiencing a runaway greenhouse effect, where increasing temperatures eventually lead to the evaporation of water and the loss of habitable conditions. While Kepler 452b's distance from Earth makes it difficult to study in great detail, its Earth-like qualities and the fact that it orbits a sun-like star make it a crucial point of reference in understanding planetary habitability. Future telescopes may be able to glean more information about this distant exoplanet. In addition, K2-18b is a fascinating super-Earth located 124 light-years away in the constellation Leo. What makes K2-18b so extraordinary is the detection of water vapor in its atmosphere, making it the first exoplanet in the habitable zone with confirmed water vapor. This discovery, made by the Hubble Space Telescope in 2019, immediately positioned K2-18b as one of the most promising candidates for further study. K2-18b is about 2.6 times the size of Earth and 8.6 times its mass, meaning it is likely a mini-Neptune with a thick atmosphere of hydrogen and helium. Despite its gaseous nature, the planet may have a rocky core and liquid water, a combination that intrigues scientists searching for signs of life. The presence of water vapor raises the possibility that liquid water exists on the planet's surface or in its atmosphere. Proxima c, another planet in the Proxima Centauri system, has also captured the attention of astronomers since its discovery in 2020. Unlike Proxima b, Proxima c orbits much farther from its parent star, making it an unlikely candidate for life as we know it. However, its large size, estimated to be about 6 times that of Earth, makes it a compelling object for study. Proxima c may have a thick atmosphere or even rings similar to those of Saturn. While it lies outside the habitable zone, studying this planet could provide valuable information about planetary formation and the dynamics of multi-planet systems. Additionally, Proxima c's proximity to Earth makes it an excellent candidate for future direct imaging missions. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. One of the most surprising discoveries in all of astronomical history occurred nearly a full century ago, when we discovered that the distant galaxies in our universe aren't stationary, but are mutually receding from one another. This realization first came about nearly a century ago, when Edwin Hubble discovered that the universe is getting larger. However, modern measurements of how fast it is expanding disagree, suggesting that our understanding of the laws of physics might be off. Everyone expected the sharp vision of the James Webb Space Telescope to bring the answer into focus. But a long-awaited analysis of the telescope's latest observations, released recently, once again gleans conflicting expansion rates from different types of data, while homing in on possible sources of error at the heart of the conflict. Two rival teams have led the effort to measure the cosmic expansion rate, which is known as the Hubble constant. One of these teams, led by 2011 Nobel winner Adam Rees of Johns Hopkins University, has consistently measured the Hubble constant to be about 8% higher than the theoretical prediction for how fast space should be expanding, based on the cosmos's known ingredients and governing equations. This discrepancy, known as the Hubble tension, suggests that the theoretical model of the cosmos might be missing something. Some extra ingredient or effect that speeds up cosmic expansion. Such an ingredient could be a clue to a more complete understanding of the universe. Rees and his team released their latest measurement of the Hubble constant based on Webb data this spring, getting a value that agrees with their earlier estimates. But for years, a rival team led by Wendy Friedman of the University of Chicago has urged caution, arguing that cleaner measurements were needed. Her team's own measurements of the cosmic expansion rate have invariably landed closer than Rees to the theoretical prediction, implying that the Hubble tension may not be real. Since the Webb telescope started taking data in 2022, the astrophysics community has awaited Friedman's multi-pronged analysis using the telescope's observations of 3 types of stars. Now, the results are in. 2 types of stars yield the Hubble constant estimates that align with the theoretical prediction, while the third, the same type of star Rees uses, matches his team's higher the Hubble constant value. That the 3 methods disagree is not telling us about fundamental physics. That's telling us there's some systematic error in one or more of the distance methods. Friedman's results have been submitted to the Astrophysical Journal, but have not yet undergone formal peer review, where outside researchers anonymously check the data and analysis. Saul Perlmutter, a Nobel Prize-winning cosmologist at the University of California, Berkeley, who was shown the team's preprint prior to its release, told Quanta that the results suggest we may have a Hubble tension just within the star-based measurements. That's the tension that we really have to be trying to figure out more than trying to invent new cosmological models. Rees, after studying the preprint, pointed out that he takes issue with the small set of supernovas that Friedman's team used in one step of the analysis, which he says could bias the results. According to Rees, the new measurements are lovely and in fact are in excellent agreement with the same measurements obtained several years ago by his group, so the distance measurements seem under control. However, this brand new study of such a small supernova sample gives a somewhat misleading impression of the value of the Hubble constant. The results come after months of behind-the-scenes drama, as Friedman initially thought her analysis had killed the Hubble tension, only to see it come roaring back to life. That's business as usual. Either ways, the Hubble constant has such a long and glorious tradition of being an impossible, decades-long problem. The hard part of gauging cosmic expansion is measuring distances to objects in space. The American astronomer Henrietta Leavitt first uncovered a way to do this in 1912 using pulsating stars called Cepheids. These stars flicker at a rate that relates to, and can therefore reveal, their intrinsic luminosity. Once you know how luminous a Cepheid is, you can compare that to how bright or dim it appears, to estimate how far away its galaxy is. Edwin Hubble used Leavitt's method to measure the distances to a handful of galaxies with Cepheids in them, discovering in 1929 that galaxies farther from us are moving away faster. That means the universe is expanding. Hubble pegged the expansion rate at 500 kilometers per second per megaparsec, meaning that two galaxies separated by 1 mpc, or about 3.2 million light-years, fly apart at 500 kilometers per second. That was wildly off. Measurements of the Hubble constant improved as astronomers got better at calibrating the relationship between Cepheids' pulsation frequency and their luminosity. However, the whole approach was limited because Cepheids are only so bright. To measure the distance to galaxies across the vastness of the universe, scientists would need a new approach. In the 1970s, researchers started using Cepheids to calibrate the distances to bright supernovas, enabling more accurate measurements of cosmic expansion rate. Then, as now, two research teams led the way, using supernovas anchored to Cepheids and arriving at disagreeing values of 50 kilometers per second per megaparsec and 100 kilometers per second per megaparsec. The 1990 launch of the Hubble Space Telescope gave astronomers a new, crisp view of the universe. Friedman led a multi-year observing campaign using Hubble, and in 2001, she and her colleagues announced an expansion rate of 72 kilometers per second per megaparsec, estimating that this was at most 10% off. Rees, who is one of the Nobel Prize-winning discoverers of dark energy, jumped into the cosmic expansion game a few years later. In 2011, his team published an Hubble constant value of 73, with an estimated 3% uncertainty. Soon after this, cosmologists pioneered another method entirely. In 2013, they used the Planck telescope's observations of light left over from the early universe to determine the detailed shape and composition of the primordial cosmos. They then plugged those ingredients into Einstein's general theory of relativity and evolved the theoretical model forward nearly 14 billion years to predict the current state of the universe. This extrapolation predicts that the cosmos should currently be expanding at a rate of 67.4 kilometers per second per megaparsec, with an uncertainty that's less than 1%. Rice's team's measurement, even as its precision improved, stayed at 73. This higher value implies that galaxies today are flying apart faster than they should be, according to theory. The Hubble tension was born. And if it's a real feature of the universe, then it's telling us that we're missing something in the cosmological model. This missing something would be the first new ingredient of the cosmos to be discovered since dark energy. Theorists have speculated about its identity. Perhaps it is an additional form of repulsive energy that lasted for a brief time in the early universe. Or maybe it's primordial magnetic fields generated during the Big Bang. Or maybe the something that's missing has more to do with us than the universe. Some cosmologists, including Friedman, have suspected that unrecognized errors are to blame for the discrepancy. The most common argument in this vein is that Cepheid stars live in the disks of younger galaxies, in regions crowded with stars, dust, and gas. So, even with the exquisite resolution of Hubble, you don't see a single Cepheid, you see it superimposed with other stars. This congestion complicates brightness measurements. When the house-size Webb telescope launched in December 2021, Rees and his colleagues turned to its powerful infrared camera to pierce the dust in the crowded regions where Cepheids live. They sought to test if crowding has as strong an effect as Friedman and other researchers have claimed. When they compared their new numbers to the distances calculated from Hubble telescope data, surprisingly, they saw phenomenal agreement. That tells us, basically, that the work that has been done with Hubble is still good. Their latest results with Webb reaffirm the Hubble constant value that they measured with Hubble a few years ago, 73.00, give or take 1.0 kilometers per second per megaparsec. However, given the crowding concern, Friedman had already turned to alternative stars that could serve as distance indicators. These are found in the outskirts of galaxies, far from the madding crowd. One type is tip of the red giant branch, or TRGB, stars. According to Kristen McQuinn, an astronomer at the Space Telescope Science Institute, who led a Webb telescope project to calibrate distance measurements with TRGBs, a red giant is an elderly star with a puffed-up atmosphere that glows brightly in red light. As it ages, a red giant will eventually ignite the helium in its core. At that moment, both the star's temperature and its brightness suddenly drop off. A typical galaxy has many red giants. If you plot the brightness of these stars against their temperatures, you'll see the point at which their brightness drops off. The population of stars right before the drop is a good distance indicator, because in every galaxy, that population will have a similar spread of luminosities. By comparing the observed brightness of these stellar populations, astronomers can estimate relative distances. However, using TRGBs as distance indicators is more complex than using CFIDs. McQuinn and her colleagues used 9 of the Webb telescope's wavelength filters to understand precisely how their brightness depends on their color. Astronomers are also beginning to turn to a new distance indicator: carbon-rich giant stars that belong to what's called the J-region asymptotic giant branch, also known as JAG-B. These stars also sit away from a galaxy's bright disk and emit a lot of infrared light. The technology to observe them at great distances wasn't adequate until the Webb era. Thus, as a strong proponent of different methods, Friedman and her team applied for Webb telescope time to observe TRGBs and JAG-Bs, along with the more established distance indicators, the Cepheids, in 11 galaxies. But what they found was truly a sort of jaw-dropping. All 3 methods gave similar distances, within 3% uncertainty. The team calculated 3 H0 values, one for each distance indicator. All came within range of the theoretical prediction of 67.4. At that moment, they appeared to have erased the Hubble tension. But when they dug into the analysis to write up the results, they found problems. The JAG-B analysis was fine, but the other 2 were off. The team noticed that there were large error bars on the TRGB measurement. They tried to shrink them by including more TGRBs. But when they did so, they found that the distance to the galaxies was smaller than they first thought. The change yielded a larger Hubble constant value. In the Cepheid analysis, Friedman's team uncovered an error. In about half the Cepheids, the correction for crowding had been applied twice. Fixing that significantly increased the resulting Hubble constant value. In other words, the Hubble tension was resurrected. But Friedman suspects that the Cepheid-based cosmic expansion rate measurement is not as trustworthy as the others. It is extremely sensitive to assumptions about, for example, the elemental composition of the Cepheids and each star's neighborhood. Dust in the galactic disks where Cepheids live can absorb their light and dim them. The Webb's infrared vision pierces the dust, but astronomers need to know how much dust is absorbing light so they can correct for it. For this, Friedman and her colleagues turned to archival Hubble telescope data, which captures the dust depth, but it's not as high resolution as Webb data. That added uncertainties in the calculated distances, she said. Another issue surfaced. The 11 galaxies they studied with the Webb telescope are the ones nearest to Earth that host all 4 relevant objects: JAG-Bs, TRGBs, Cepheids, and the relevant type of supernova. But according to Friedman, the galaxy's supernovas seem to be intrinsically brighter than the ones in farther galaxies. Rees and his colleagues also are concerned that this sample may be misleading and biased. In any case, it is another puzzle cosmologists have yet to understand, and it also affects the Hubble, a constant value. Luckily, the James Webb Space Telescope is also enabling additional ways to measure the cosmic expansion rate. For instance, astronomers are in the early phases of using how modeled a galaxy looks as a proxy for its distance. The idea is simple. Closer galaxies look clumpier because you can resolve some of their stars, whereas more distant galaxies appear smoother. It's basically a way to turn the crowding into a measure of distance. A different method also offers some hope. A massive cluster of galaxies acts like a warped magnifying glass, bending and magnifying the image of an object behind it and creating multiple images of the same object as its light takes multiple paths. The University of Arizona astronomer Brenda Fry leads a program to observe 7 clusters with the Webb telescope. When Fry and her colleagues looked at their first telescope image last year, featuring the massive galaxy cluster G165, we all just said, "What are those 3 dots that weren't there before?" she recalled. The dots were 3 separate images of the same supernova that had exploded behind the cluster. After repeatedly observing the image, they could calculate the differences between the arrival times of the 3-lensed supernova images. The time delay is proportional to and can be used to infer the Hubble constant. Researchers measured an expansion rate of 75.4 kilometers per second per megaparsec, although with a large uncertainty of plus 8.1 or 5.5 kilometers per second per megaparsec. The team expects to refine those error bars after a few more years of similar measurements. In short, the next few years of James Webb's observations will enable researchers to home in on an answer with their traditional star-based methods. With the improvement in the data, this is ultimately going to be solved, and I think pretty quickly. We're going to get to the bottom of this. Another interesting puzzle. Many cosmologists believe that the expansion of the universe is accelerating. If so, here on Earth, why don't we feel the universe's expansion, or feel the expansion accelerating, where we are right now? The surprising answer is that space isn't expanding everywhere, and that includes here. The first physics equation that most people learn isn't Einstein's E equals mc squared, even though that's arguably the most famous equation of all time. Instead, the first and arguably most important equation that gets to the core of physics goes back to Isaac Newton and is F equals ma, where F is force, and specifically is the net or total force acting on an object. M is mass, specifically the mass of the object that the force is acting on, and a is the acceleration of the object subjected to that force. It tells you a number of important things that are occurring. It first says that if you have an object that no net force acts on, where the net force is 0, that object will not accelerate, and instead will remain in constant, unchanging motion. The core idea behind Galilean relativity. It tells you that if there is a net force acting on you, that this force will change your motion, causing an acceleration that's not only in the direction of the net force, but of a magnitude that equals the magnitude of the force divided by the object's mass. And, because it's an acceleration that's caused by the force, it tells you that the longer that force remains applied, the more the object's velocity and distance will both change in the direction in which it accelerates. This Newtonian picture of reality is extremely successful in many realms, on Earth, on other planets, all throughout our solar system, in stellar systems outside of our own, and all throughout the galaxy and even beyond. When objects accelerate, that is, when their velocity changes with the passage of time, it's because there is a net force acting on them, and that force is the cause of their acceleration. And furthermore, The magnitude of the acceleration of that object is given by the magnitude of that net force divided by the accelerating object's mass. This is true for all of the forces in nature: the gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Humans, whenever we jump and our bodies leave the ground, we accelerate downward toward the center of the Earth because of the force of gravity from the Earth. The Moon, even though it's hundreds of thousands of kilometers away from the surface of the Earth, also accelerates downward, or toward the center of the Earth, because of the net force acting on it, the force of gravity for the Earth. However, and this is important, the acceleration of a human near the surface of the Earth and the acceleration of the Moon, some 380,000 kilometers farther away from the surface of the Earth, are not the same. The Moon accelerates much more slowly toward the center of the Earth than a human who jumps, whether from level ground, off of a cliff, or out of an airplane, because the force of gravity gets weaker with greater and greater distances. In fact, this is true of all of the fundamental forces of nature. The greater the distance is between any two objects that there's a force or interaction between, the weaker the strength of the force or interaction becomes. In fact, if the Moon were only half as far away from the Earth, the gravitational force acting on it would be quadrupled. Twice as far away from the Earth, the gravitational force acting on it would be quartered. 10 times as far away from the Earth, the gravitational force acting on it would be just 1/100th, or 1%, of what it is at present, and as the force changed, because the Moon's mass is unchanging, so too would its acceleration toward the center of the Earth change in the same fashion. However, we've sent astronauts to the Moon itself, and had them both orbit around the Moon as well as land and walk on its surface. Despite how great the gravitational force of the Earth is, and despite the fact that the Moon actually changes its distance from Earth substantially, an astronaut on the Moon doesn't feel the gravitational force from the Earth at all. There is no experiment or measurement they can perform, from dropping feathers and hammers to moving their bodies to conducting studies of motion using high-tech accelerometers, that allows them to detect the Earth's gravitational force acting on them. There is a reason for this. From the point of view of an astronaut on the Moon, the laboratory of being on the Moon is itself an inertial frame of reference. Sure, the Earth tugs on the Moon, just as surely as the Sun and the other planets also gravitationally tug and exert a force on the Moon. But remember what Newton's equation, F equals ma, actually tells us. It tells us that, while the force on an object is proportional to its mass, the acceleration of that object is not. The acceleration is actually the force on that object divided by its mass, Fm. When the Earth pulls on an astronaut on the Moon, it exerts a smaller force on the astronaut than it exerts on the Moon, but the force is smaller in proportion to the astronaut's mass. In other words, the Earth causes the astronaut to accelerate by the exact same amount that it causes the Moon to accelerate. Similarly, the Sun, and all of the other planets besides Earth, also cause both the Moon and an astronaut on the Moon to accelerate at the same rate, even though the forces on them are vastly different. Because both the astronaut and the Moon are accelerated uniformly, at the same rate, by the external forces acting on them, an astronaut on the Moon only experiences the gravitational force of the Moon itself, in terms of the net force acting on it. Similarly, once any object is dropped, including the famous hammer and feather experiment performed during Apollo 15, it's the force of the Moon's gravity, not influenced by the Earth, Sun, or anything else, that determines the rate at which those objects accelerate downward and fall. The reason this notion of F equals ma is so successful on the scales that humans experience, including on terrestrial, solar system, celestial, and even galactic scales, is that we are restricting ourselves to considering systems that are bound together by one of the fundamental forces. But this is no longer true on cosmic scales. There are important assumptions that normally go unstated whenever we talk about Isaac Newton and a Newtonian view of the universe. In particular, Newton assumed that forces rule the entire universe, that the gravitational force was instantaneous, that it acted at a distance between objects, and that distance was some value that could be known in an absolute and objective fashion, and that it occurred between all objects that had a mass. All of these assumptions, as true as they seem, were overturned once Einstein came along. Gravitation can be viewed as a force under many circumstances, but it's also more than a force. It's a consequence of the fact that mass and energy, not just mass, curve the fabric of space-time itself and cause that fabric to evolve, and then that curved, evolving fabric tells matter and energy how to move. The gravitational force isn't instantaneous, but only propagates at a finite speed, the speed of light. And distance is not absolute, but is rather relative, as objects in motion experience and measure distances to be contracted along the direction of motion relative to objects that are instead at rest. These realizations led humanity to abandon this wholly Newtonian concept of forces and accelerations as being linked by F equals ma, at least under all circumstances. Instead, a more universally acceptable concept is given by Einstein's general theory of relativity, which relates the concept of space-time, which can be curved and can evolve in many ways, including by either expanding or contracting, to the distribution and motion of the masses and other quanta and forms of energy present within that space-time. When things are approximately Newtonian, such as when you have a gravitationally bound system that you're considering with masses moving at speeds slow compared to the speed of light, and where there are no extremely dense concentrations of matter, including black holes and neutron stars, then it makes sense to use F equals ma, as Newton's conception of reality comes very, very close to producing exactly the same predictions as Einstein's much more labor-intensive predictions. This approximation works very well on scales of planets, stellar systems, stars, individual galaxies, and even isolated groups and clusters of galaxies. The largest such system that we're a part of is our local group of galaxies, which includes the Milky Way, Andromeda, and more than 100 other smaller galaxies all bound together. The local group extends for approximately 5 million light-years, and when objects within this group of galaxies accelerate relative to one another, it's because of a gravitational force. That is something we can measure and quantify, no doubt. But the expansion of the universe, once you go to scales larger than that of a gravitationally bound structure, is not a Newtonian construct, and no longer obeys the notion of F equals ma. This is a phenomenon that is exclusive to general relativity, and arises whenever you have a system that obeys the Einstein field equations under conditions where the energy within your system is, roughly, uniformly distributed all throughout space. No longer are accelerations, where you can measure the change in the speed of a distant object over time, determined by forces, but instead whether an object accelerates or not, as well as how quickly it accelerates or decelerates, is determined by all of the different types of energy present within your universe. In our universe, we can measure how quickly distant objects appear to be receding from us, as we can infer a recessional velocity from the observed redshift of those objects. We can see how the redshift-distance relation behaves as we look to more and more distant objects, giving us a clue to how the universe's expansion rate has evolved over time. And we can use a variety of cosmic probes to determine what the various forms and densities of energy within the universe are. When we put this all together, we arrive at a consistent picture of our own cosmic history, complete with an understanding of what the universe is made out of, both now as well as at all moments in our cosmic past. Today, our universe is dominated by dark energy, a novel form of energy whose nature is ultimately unknown, but that appears to be most consistent with a cosmological constant, or a form of energy that's inherent and intrinsic to space itself. This is important because it's the sum total of all the different forms of energy that tells us how the universe expands, and how those different forms of energy evolve over time tells us how the distances between two unbound objects, as well as the inferred recession speeds between those objects, will evolve over time. There are three classes of energy in the universe that are important for these purposes. There's radiation, or particles that move at or near the speed of light, which includes photons and neutrinos. As the universe expands, the number density of these particles drops proportionally to the volume of the universe, i.e., as size distance cubed, multiplied by another factor of size distance as the wavelength of the radiation gets stretched within the expanding universe as well. There's matter, including normal and dark matter, whose density drops proportionally only to the volume of the universe, as size cubed. There's dark energy, which we assume to be a cosmological constant, although that may only be approximately true, whose density remains constant over time. In a universe that contains all three, there will be three stages to any expanding universe: an early, radiation-dominated stage, where the expansion rate drops quickly over time; a middle stage, dominated by matter, where the expansion rate still drops over time, but not as quickly as during radiation domination; and then a final stage of dark energy domination, where the expansion rate ceases to drop, and instead remains at a finite, positive, non-zero value. The implications of a universe exhibiting this behavior, with radiation, matter, and dark energy within it, are profound. It means that the expansion rate, which we measure as a speed, kilometers per second, per unit distance, per megaparsec, will drop when radiation and matter are dominant, but will only approach a constant positive value when dark energy is dominant. And it means that the inferred recession speed of a distant, unbound galaxy is dependent both on the expansion rate at any moment in time and also on the distance to that galaxy. When radiation and matter are dominant, the observed recession speed goes down over time, and so we say the expansion decelerates, because the speed at which the galaxy appears to be moving away from us, in terms of kms, appears to be going down over time, or dropping. But when dark energy is the dominant factor in causing the universe to expand, something that first happened about 6 billion years ago, the observed recession speed goes up over time, as the speed at which a distant, unbound galaxy recedes from us appears to increase with time. Even though the expansion rate isn't increasing, the recession speed appears to go up as the distance to the galaxy increases, and so we say the expansion accelerates. But don't fall for a common misconception. This cosmic acceleration is not the consequence of a force. It is a consequence of the presence of dark energy, a form of energy inherent to space itself within the expanding universe. The reason it wasn't discovered until the 1990s is because we cannot measure it in a laboratory here on Earth, but only by looking to the extremely distant galaxies present throughout the visible universe. On cosmic scales, we can still have acceleration, but we can no longer chalk any of it up to the classic F equals ma given to us by Isaac Newton back in the 17th century. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.